All right. So continuing in our line of applications of multi-calibration, today I want to talk about distribution shift. And maybe just to sort of situate that, thus far we've sort of talked about two extremes of where the data might come from. Okay, we've talked about sort of the batch setting, where we get somehow, for example, IID samples from some distribution. We have the luxury of training a model on that distribution and can verify that we've succeeded in training a multi-calibrated model, for example. And then when we prove generalization guarantees, what that means is that we prove that our model has the properties it says it does, not just on the data we trained it on, but on new data drawn from the same distribution. Okay, so this is sort of a setting where we've assumed something very nice, which is that we got to train data, we got to train our model on data that came from some well-behaved source, like points were drawn IID from it, and that this source didn't change between training and test time. Okay, so that was like one thing we've studied. Another thing we've studied is sort of the opposite extreme of that, right? The like fully adversarial model, where not only can the distribution change in arbitrary ways, as we go on, there doesn't have to be a distribution at all. Like when we give guarantees in the sequential adversarial setting, we assumed nothing at all about the data generating process. But we did have to assume something pretty strong about the data access model, which is that at every round, after we made a prediction, we learned what the label was. Right, and that was sort of important, right? Like the way our algorithms worked is every day they made a prediction, they learned what the label was, and then they updated their state. Okay, so on the one hand, this moved quite far away from sort of the IID setting, like the data could come from some arbitrary adversarial process. On the other hand, we had to sort of assume that labels were available shortly after we needed to predict them, which is true in some settings. Like if we're talking about stock prediction or other time series settings, we predict something and then we learn what happens. But it's not always true. And so what we'd like is, ideally to get the best of both worlds. Somehow we'd like to be able to train a model on data drawn from one source and then deploy it and have it have guarantees on data drawn from some other source, even though we cannot get labels from that second source at deployment time. That would be like the ideal. Now, it's sort of plainly impossible if we assume nothing at all about the relationship between our sort of training source and our test source, because, for example, they could be entirely opposite of one another, right? It could be that examples that have positive labels in the training data are exactly those examples that have negative labels in the data at deployment time. And if we can't rule that out, then we can't rule out that if we do anything at all like what we trained on, that we're sort of maximally bad. Okay, so it's like plainly impossible to have the best of both worlds, to be able to sort of handle arbitrary shifts without getting any feedback about what the labels are at test time. But maybe there's some middle ground. Maybe we can do something if we don't assume that if we don't sort of assume that the shift is sort of totally worst case, but instead has some structure. So that's what I want to do in this lecture. And in particular, what I want to assume is that the underlying relationship between features and labels remains the same between sort of training and test. Okay, like the distribution on features might change, but I want to assume that there is some fundamental ground truth, which is the conditional label distribution given the features, that is at least possible to learn in principle and invariant. So the distribution might be different between training and test, but like at least we're not completely out of luck. There is a thing to learn that doesn't change. That's the relationship between the features and the labels. Okay, so this is let's formulate this as an assumption. So we'll say that two distributions and when I talk about two distributions in this lecture, I'll sort of call them ds and dt for source and test. And I'll, just to sort of foreshadow, I'll generally be imagining that we are training on the source distribution and then deploying on the test distribution. Two distributions have the same conditional label distribution. If for every feature vector, and I'm also assuming these distributions are of the same, defined over the same domain. If for every feature vector, if I look at the conditional label distribution at X, it's the same as the conditional label distribution at T. Or sorry, if I look at the conditional label distribution under distribution S, conditional on X, that is the same as the conditional label distribution, also conditional on X for distribution T. Okay. So i.e., they differ only in their marginal feature distributions. Okay, so the two distributions might have very different distributions on features, but for any particular feature vector, once you fix the features, that induces the same conditional label distribution. Yeah.
But we're only promising this for two vectors that are exactly the same in feature.
That's right.
Okay.
Mm-hmm. Yeah, so we're not making any assumption about, first of all, like what this conditional label distribution is, and sort of the relationship, right? Like we're not assuming that it is Lipschitz in X, for example.
Yeah.
But we are assuming that, like, in principle, there's some commonality that we can learn between these two distributions, and that is, okay, what are the labels given the features? Okay, and for example, if you believed that the labels were causally related to these features and that we hadn't left out any causally relevant features, then this is the kind of thing you would expect. Okay, that you might have sort of different distributions on treatments, but if I tell you everything that is causally relevant to the label, then the label distribution is fixed. Okay. So for the rest of this lecture, I'm going to talk about distribution shift for pairs of distributions ds and dt that have the same conditional label distribution. So even though I won't write it out for every lemma and theorem and corollary, one of the preconditions will be the assumption that these two distributions ds and dt have the same conditional label distribution. So if I've got two distributions that have the same conditional label distribution, and now I want to talk about how these two distributions are different from one another, right? I can focus on how the marginal probability on any particular feature vector differs across the two distributions. That's the only thing that is different across the two distributions. And a useful quantity for translating statements from one distribution into statements about another distribution are going to be what are called likelihood ratios. Okay, so related to propensity scores, if you've come across those. Okay, so let's define likelihood ratios. So for each feature vector, let's say that PS of X is the probability under distribution S of observing X. Okay, so if it's a discrete distribution, this is the probability density function, or the probability mass function. If it's a continuous distribution, it's the probability density function. In general, since I prefer sums to integrals, I'm just going to assume that everything we talk about today is a discrete distribution, but that's not actually important. Okay, so PS, that's the probability of X under distribution S. Similarly, PT is the probability under distribution T of observing feature vector X. I'll write it this way: the S to T, S arrow T, likelihood ratio for X is this quantity, which I'll write as W S to T of X. It's just the ratio of the probability of X under T to the probability of X under S. Okay, so it's like bigger than 1 if this particular observation is more likely to occur under distribution T. It's less than 1 if this particular observation is more likely to occur under distribution S. Okay, and observe. Like, it's not symmetric. This is, the S to T likelihood ratio, but right, the S to T likelihood ratio, it's the ratio of the probability of X under T to the probability of X under S, and the T to S likelihood ratio is the reverse probability. So, one thing that's sometimes useful is just to note that 1 over the S to T likelihood ratio is the T to S likelihood ratio. Okay. Okay, so these are like some quantities that are well defined no matter what the two distributions are, at least so long as the denominator is not 0. Okay, so like in principle, these ratios could be undefined or infinite if there's some X that like can occur under distribution T, but just like occurs with probability 0 under distribution S. But so long as both of these distributions have some support, have positive support everywhere, these are sort of well defined for any pair of distributions that agree on their conditional label distribution. And in fact, if the distributions agree on their conditional label distribution, then if I know one of these distributions, if you also tell me the likelihood ratio, I also know the other one. Okay. So why are these things useful, and why have I chosen to write, the particular choice of putting the probability density of T in the numerator as the S to T likelihood ratio? Well, it's because if I want to compute an expectation under T, under distribution T, but I only have access to samples from distribution S, then I can compute my expectation under distribution S, but reweight points using this likelihood ratio, and that will give me in expectation the correct answer under distribution T. Okay, so this is a weighting that lets me compute things under S, but derive answers that are sort of as if I computed them under T. Okay. So suppose I've got two distributions that have the same conditional label distribution. Let's prove a sort of general version of this statement. For any subset of the feature space and any function f that maps both features and labels to numbers if I compute the product of the probability that S lands in S, compute this under the source distribution, times the expectation, again under the source distribution, of the S to T likelihood ratio of X times F of XY, conditional on X lying in this set S. This is equal to what I would have gotten if I had computed the probability of lying in this set S under the test distribution times the expectation, again under the test distribution, of F of XY, conditional on lying in this set S. Okay, so let's just sort of internalize what this is saying, and we'll prove it. It's pretty immediate. But it's saying, look, there could be any arbitrary function of the features and the labels. And perhaps we're interested in the conditional expectation of this function over the test distribution, conditional on X lying in any subset of the feature space. Okay, so any F we want to estimate, conditional on any event defined over the feature space. We want to compute this over the test distribution, but if instead we compute it over the source distribution, and appropriately reweight things by multiplying by these likelihood ratios, then actually we get the same answer. Okay. Statement clear? Okay. So it's pretty immediate, but let's write it out, write out the proof to just get some feel for what these likelihood ratios are doing. So we're computing this thing at the top. The probability under the source distribution of landing in this set S times the expectation under the source distribution of the likelihood ratio of X times F of XY, conditional on X landing in S. Well, assuming this is a discrete distribution, we can just write this as the sum. And if it were a continuous distribution, we would just write the sum a little bit less sharply, so it was an integral. The sum over all of the points in this set S well, it's an expectation. So the probability of observing that point times the thing we're taking the expectation of, which is the S to T likelihood ratio times, well, we have to not forget about the randomness over Y. So times, here we've sort of expanded out the expectation over X, but really this is an expectation over both X and Y, because Y shows up in here. So times the expectation over Y drawn from the conditional label distribution given X of F of XY. Okay, and note here I've just said the conditional label distribution given X. I haven't said from S or T. Well, we've assumed that S and T have the same conditional label distribution. So there is like one conditional label distribution common to both of them. Okay, so all that's happened here is, we've started from this expression. We've noted actually this is an expectation over X and Y. We're just expanding out the expectation over X as the probability weighted sum over points in X. We're still taking the expectation over the randomness of Y. Okay, but what are these likelihood ratios? Well, the likelihood ratio is just the ratio of the probability of seeing X under T over the probability of seeing X under S. Okay, and so conveniently, the probability of seeing X under S, which is in the denominator of the S to T likelihood ratio, cancels out with the probability of seeing X under S, that is the weighting in the definition of taking an expectation under S. So these terms cancel out, and we get that we have the same sum, except now without the likelihood ratio, and where all of the terms are weighted by their probability under T rather than their probability under S. Okay, but now this is just an expectation over X where we've expanded it out as a weighted sum. And so we can rewrite this as the probability now under the source distribution, or rather the test distribution, that X is in S times the expectation under the test distribution of f of xy conditional on X being in S. Make sense? Okay, so this is why these likelihood ratios are useful, right? Like sort of at this crucial moment where we need to switch from distribution S to distribution T, well, that corresponds to switching the weighting in this sum as a weighting under S to a weighting under T, and the likelihood ratio is exactly the thing we need to multiply to swap those weightings. Yeah.
We also are like relying on the conditional label being the same.
That's right. So,
otherwise, you don't have any subscripts.
Exactly. Yes. So, in order for this to be true, and so like an unstated assumption in this lemma, and for every lemma I will prove subsequently in this class today, is that these two distributions have the same conditional label distribution. Yeah, in general, if the conditional label distributions can differ, then this reweighting is not going to be enough. And if they can differ in ways that are arbitrary, then you're kind of out of luck. But yes, this is under the, these likelihood ratios are useful primarily when the sort of relationship between any particular X and its labels Y is fixed across these distributions, and it is just the frequency of the different X's that is different. Okay, makes sense. Okay. So frequently, so like, where do these likelihood ratios come from anyway? Like, generally, we do not know what is the probability, like what are these distributions? We just have samples from them. Okay. And oftentimes, in a machine learning or statistical estimation setting, you will have labels from the source distribution, but not from the test distribution. Like from the source distribution, you had labels because you trained some model to do something. You learned a regression, you learned a multi-calibrated predictor. You needed labels to do that. But then the whole point of the test distribution is you don't have labels and you're hoping to predict them. And so you sort of, what do you have on hand? You've got source data, feature label pairs, and maybe you've got unlabeled test data, X's from the test distribution, but no labels. If you had labels from it, you could just learn something on the test distribution. Now these likelihood ratios, they don't depend on the Y's. So you can try to learn them just from unlabeled data on the source and the test distribution. Okay, and that's sort of a standard thing to try to do, to try to learn likelihood ratios like this. Of course, you're not going to get them exactly. You're going to get, at best, some approximate versions of them. So maybe it's useful to think about how and in what metric error in estimating these likelihood ratios propagates into sort of error for other downstream estimation tasks. Okay, so again, suppose we've got two distributions, S and T, that for which it makes sense to talk about likelihood ratios. So they agree on their conditional label distributions. Let's define the following error metrics. Okay. So we wanted to come up with these likelihood ratios. So we learned some function h that we're hoping is equal to this, but probably isn't exactly. So we've got some function h. It's some mapping from feature vectors to real numbers. Like we're crossing our fingers, we're hoping it's the S to T likelihood ratios, but maybe it's not. Let's say that the error, our estimation error in estimating the S to T likelihood ratios with H is the expectation under the source distribution of the absolute value difference between H of X and the thing we were trying to learn, the S to T likelihood ratios. And similarly, for any subset of the feature space, let's say that the error of our estimate H in trying to estimate these likelihood ratios on this subset of the feature space is the expectation, again, under the source distribution of the absolute value difference between H of X and the thing we were trying to learn, but now conditional on lying in this subset of the feature space. Okay. So it's like a measure of like total variation distance or statistical distance. It's like on average, how incorrect are our estimates when we're taking the average over the source distribution. Okay, so it's okay, like, it's weaker than sort of a pointwise bound. Like it might be okay if we are sometimes really, really off, so long as we're not really, really off too frequently. Okay, like on average, if I pick a random point, I want to be close to the thing I was trying to learn. Okay. And maybe one thing to note, just from the law of total probability, if I've got a collection of sets, call them S1, through SK that form a partition of the feature space, then if I sum over all of the elements of the partition of the probability, I land in that element of the partition times my estimation error of the likelihood ratios in that element of the partition. This is just my overall estimation error. Okay, so this is some way we could measure the error of having estimated some likelihood ratio function. If we get it exactly, the error is 0. If we don't get it exactly, the error is greater than 0. And here we're measuring how wrong we are, like on average. That's maybe the thing to note rather than in the worst case. Okay. So this is kind of the right measure for error if the thing that we're trying to do with likelihood ratios is this. Like if the reason we were interested in these likelihood ratios is because we wanted to estimate quantities that look like this over the distribution T. And our plan was to do that by estimating quantities that look like this under the distribution S. Then if we do that with some function h instead of with the true likelihood ratios, we will have accomplished what we wanted up to estimation error proportional to this. Yeah.
So the expectation here is over the source.
That's right.
It's like, what the important distribution is the first one.
Well, they're both important, but this is,
Like I'm saying that let's just imagine that on the test distribution, like almost all weights are in some part, and for the source distribution, it's the opposite, right?
Mhm.
And then like is estimated error is just like very small. It can be very small, but like in real world or on the test distribution, we're not performing the well.
So that's true. I mean, so you're pointing out, if nothing else, that I could also evaluate this under the test distribution, and that would be a different number. That's true. Unfortunately, that number would not be as useful in controlling the relationship between the thing I was trying to estimate and the thing I was really estimating. You could work out, if you wanted, by the way, like some error metric that was defined as an expectation over the test distribution rather than the source distribution, right? Because we know a relationship between expectations over the test and source distribution. They're sort of controlled by the likelihood reweighting. So if you wanted to have an error metric that was defined as an expectation over the test distribution, you could transform this into one, but it would be ugly. It wouldn't be a simple, measure of L1 error like this. And so sort of we'll see in the short proof that this is the quantity that sort of controls the error in this estimation task. Essentially because the estimation task we're actually performing, right? We're trying to estimate something over T, but the thing we're actually estimating is an expectation over S. And so sort of the thing we're concerned about is how different our reweighting function is from what it was supposed to be over S.
Maybe understand the issue that they're pointing out, which is, but I think the problem is that if you have an area of your source distribution that has 0 support, that has very high support in your target distribution, then if h and of x and your likelihood ratio are very different from each other, you won't pick any of those things up in that quantity, right? But I guess I still don't see why that's okay.
So you're pointing out a situation where this could be very small, maybe even 0, and the corresponding expectation over t would be large.
Or like, yeah, so if there's spots where your h of x is making terrible mistakes, the
Mhm.
likelihood.
Yeah, so there could be like, it could be that there are points x that have like 0 probability mass under S. Such points, well, okay. Let's not say 0, because then these likelihood ratios aren't even like super well defined, but let's say, teeny tiny. Okay, so, under S, they have teeny tiny probability mass. So these like likelihood ratios are super duper humongous, but we didn't make H like super duper humongous enough. So maybe like there's like big error on those points, and maybe those points are actually pretty likely under T. And so if we took this expectation over T rather than over S, it would be a big number, whereas it's a small number when we take it over S. That could happen, but it wouldn't matter for, like, it wouldn't contribute a lot of error to our estimation here, because the estimation we're actually doing in the top line here is an expectation, it's a expectation over S. So sort of large amounts of error that only have very small probability mass under S won't contribute too much. So maybe it'll be clearer when we prove that, but
Yeah, that makes sense. It just feels like counterintuitive to what we're trying to do.
well, to be clear about what we're trying to do, what I want to do is have just a version of this statement saying, look, here's a thing we can estimate under S, and I'd like it to translate into knowledge about something under T. But without sort of, the thing that we estimate under S, I don't want to assume I have like perfect likelihood ratios. I want to say, look, if they're imperfect in some way, then the error will propagate to the thing I was trying to estimate. And the claim that I'm going to make and then prove is that this metric is a good way of measuring how that error will propagate. And that is despite the fact that, as you point out, it might be the case that my estimate of the likelihood ratios is very wrong on points that appear frequently under distribution T, and that's okay so long as the points don't appear too frequently under distribution S. And it's basically because we're taking the expectation over S. Okay. So what's the claim? Suppose we've got two distributions, S and T, that have the same conditional label distribution as always. For any subset of the feature space and any function from features and labels to numbers, and any weighting function from features to numbers. Suppose what I do is I compute this quantity, except I don't use the true S to T likelihood ratios. I use H instead. Okay, so I compute the probability under the source distribution of lying in this set S times the expectation under the source distribution of H of X times F of XY, conditioned on lying in this set S. And I, cross my fingers, close my eyes, and wish that this is equal, hopefully, So the expectation under the target distribution, or the probability under the target distribution of lying in the set S times the expectation under the target distribution of f of xy conditional on lying in S. Okay, I hope these things are the same. And I'm interested in how wrong I can be. And if I had, what our old lemma said is that if H was exactly the likelihood ratios, then these two quantities would be the same. And what we're going to say now is that even if H is not exactly equal to the S to T likelihood ratio function, I can bound the error by, well, the size of this set S, the probability that I land in S, times the scale of this function f. And right, the error could get bigger if f takes like truly enormous values. So I need to have a scale term in here, the maximum absolute value this function can take over any input, times the estimation error as we just defined it between H and the likelihood ratios on this set S. This is the probability under the source distribution. Okay. So it's saying, suppose we weren't conditioning on anything. So the probability of S was 1. S was everything. And suppose, F was bounded between 0 and 1, say, so it's a normalization. This is saying that we could bound our estimation error of trying to estimate this quantity under T when actually we estimated it under S using H instead of the likelihood ratios by exactly this measure of estimation error here. Right. Okay. So let's observe this. So we want to look at the difference between this expectation defined over S and this expectation defined over T. Now, we already know how to relate expectations defined over T to expectations defined over S. We relate them using the likelihood ratios, right? So I can think of this term on the right as an expectation not over T, but rather as an expectation over S, where now I've weighted the thing inside the expectation by the correct likelihood ratios. Right? That's what the correct likelihood ratios do. They convert terms that look like this, where the randomness is over S, to terms that look like this, where the randomness is over T. Okay. So this difference, it's equal to the probability under S of the set S times the expectation under S of H of X times F of XY minus the S to T likelihood ratio. of x times f of xy. Conditional on x lying in S. Right? Like all I've done is I've said, okay, if I want to view this as an expectation not over T, but over S, the way that I do it is I just reweight these terms by the likelihood ratio, the S to T likelihood ratio. Now, both of these things are expectations over S, and so I can combine them into the same expectation, where on the left, I've got this quantity F reweighted by H, and on the right, I've got this quantity F reweighted by the true S to T likelihood ratio. Okay. Or, just combining terms a little bit. Just the expectation under S of f of xy times the difference between h of x and the true S to T likelihood ratio. And so we want to upper bound this. Okay, so we still have the probability that x is in this set S. And then inside this expectation, we've got the product of these two terms, and either one of them could be positive or negative, right? Like f of xy, it doesn't have to be positive, it could be positive or negative. H of x could be bigger than the S to T likelihood ratio, or it could be smaller. So this difference could also be positive or negative. So it's not like we can, sort of, we can't ignore signs. But, like in the worst case, they both have the same sign. Right, so we can certainly upper bound this by, well, first of all, the maximum value the maximum magnitude that f of xy could possibly take, times the expectation under the source distribution of the absolute value of h of x minus the S to T likelihood ratio. And this is just the definition. That we gave over here of the estimation error that H has with respect to the likelihood ratios on set S. Okay, makes sense.
So you drop those absolute value signs on the outside of the whole thing, but because, right, like the original expression, you have absolute values of the difference. Really, all you've done is you just move those into the, like h of x minus w minus the likelihood ratio. That difference is the only thing that could ever be negative anyway. So it's not even good.
Yeah. Like, I guess you're saying, like, initially, yeah, like there should be like absolute values outside this whole thing. Okay, first of all, no problem having the probability of S be outside the absolute values, because that's definitely a positive value. Yeah, and we're sort of saying, okay, moving the absolute values inside the expectation only makes things bigger, because that disallows cancellations that might have otherwise happened. And assuming that f of xy and h of x minus the S to T likelihood ratios have the same sign only makes things bigger, because they could have had different signs, which is equivalent to putting absolute values on the individual terms on the inside. Yeah, and then we've just sort of upper bounded f of xy by its maximum possible magnitude. Okay, good. So to the extent that we can control this metric, we are good to go in terms of using H in place of the true S to T likelihood ratios, because, if we want to use H to estimate expectations under T using data from S, H will do it up to error controlled by this estimation error metric. Okay. So, so far so good. Like, this is just fun facts about likelihood ratios, nothing about multi-calibration yet. Like, we're just sort of saying, okay, if you want to estimate something from like a source about a target distribution from a source distribution, like you want to learn likelihood ratios. And if you learn likelihood ratios, which you can try to do just from unlabeled data, you don't have to do it exactly, so long as it's controlled in this metric, you have approximate guarantees. And sort of a traditional method of out of distribution estimation is to do that, to try to estimate likelihood ratios for your particular source and target distribution. But that sort of takes active effort every time you come up with a new target distribution, right? You get new samples from a new target distribution, then you've got to try to like re-estimate these S to T likelihood ratios, which are now different numbers. And then you can, go back and try to estimate things for this target distribution, but sort of whatever effort goes into learning these likelihood ratios is repeated every time you have a new target distribution. So what we'd like to do is we'd like to say, look, and also you have to sort of be very intentional about doing this like out of distribution estimation. You can't just take your expectations, like verbatim, you've got to like reweight them explicitly. Okay. So what we'd like to do is two things. We'd like to have a way of learning models that are, on the one hand, sort of automatically good at estimating things out of distribution. And we don't want to have to, in learning those models, have to know exactly what the test distribution is. We'd like to be able to learn some model using data from S that is good for estimating things for a whole class of test distributions T, not just one particular test distribution. Okay, so we'd like to learn one model up front on S that is going to be simultaneously good at allowing us to estimate things, we'll be clear about what things exactly, on test distributions T without knowing what they are ahead of time. Now, of course, we can't be good at estimating things on all possible test distributions, and that's not what we're going to promise, but we'd like to promise that our model is good for all test distributions in some family. And that's what we're going to try to get at through multi-calibration. Okay. So the flavor of multi-calibration that's going to be most convenient for us is, like this L1 measure of multi-calibration. So sort of remember, whenever we've given a multi-calibration distribution, or at least at the beginning, we sort of noted, look, there's different ways of measuring multi-calibration error. You can measure like L1 error, like average absolute error, or L2 error, average squared error, or L infinity error, maximum error. These are averages or maximums over the level set of the predictor. And in analyzing algorithms, it has often been most convenient for us to analyze the L2 notion of multi-calibration. That was what was sort of the most natural potential function. But in this application, the statement about multi-calibration that will be most directly useful is the statement of L1 multi-calibration, which I'll remind you of the definition now. What I want you to remember is that at the very beginning of class, we proved simple relationships between these different measures. So if you can drive one of them to 0, you can drive the other one to 0. So we've given algorithms for driving L2 multi-calibration error to 0 for some class of functions H. The same algorithm drives L1 multi-calibration error to 0 because they're closely related. Okay, so here's the definition of L1 multi-calibration for real valued functions, right? So remembering back to last lecture when we studied multi-calibration for real valued functions, we're going to continue with that kind of definition, except now we'll give the L1 variant. Okay, so fix the distribution D. A model F features to numbers between 0 and 1. And a set H of functions H from features to real numbers. Okay. Think maybe of these functions H as the kind of functions that you might want to use to approximate likelihood ratios. We say that F is alpha approximately L1 multi-calibrated. If for every function little h in our set, the K1 measure of calibration error on H, which just to remind you, is the average over all of the predictions in the range of our model F. Of the absolute value difference rather than the squared difference. This is the difference between L1 and L2 calibration error. So the absolute value difference, or the absolute value in this case, of the expectation of h of x times y minus v, given that the predictor takes value v, should be less than alpha. And similarly, this is like multi-calibration. We can also talk about L1 calibration, which just doesn't have this class of functions H. Doesn't have this class of functions H. That's just the statement that the expectation over the level sets of F of the expectation of y minus v conditional on landing in the appropriate level set of F is less than alpha. Okay, so just to sort of remind you, last class when we talked about boosting, we gave a definition of L2 multi-calibration for real valued functions, which was exactly this definition, except instead of absolute values here, we had a square. Okay, and just to remind you, this is something we proved, I think, in the very first class. The L1 multi-calibration error can always be upper bounded, this is like Cauchy-Schwarz inequality, as the square root of the L2 multi-calibration error. Okay. So like last class, we gave an algorithm that, given a regression oracle for H, drove the L2 multi-calibration error to 0. And so it also drives the L1 multi-calibration error to 0. And so this is not just like a totally random definition, but one that we already know how to satisfy. Okay. So this is just like the L1 variant. That's the one that's going to be most convenient for us here. And so the first thing I want to, okay, so, okay, what's the plan? I want to say eventually that if your model is multi-calibrated with respect to some class of functions H that contains a function that is close to the propensity score or the likelihood ratio, the S to T likelihood ratio, and you're multi-calibrated with respect to H on S, that your model is still useful for some stuff on T. Okay. So we'll have to talk about what stuff, but the first thing I want to do towards getting to a statement like that is translating multi-calibration with respect to some class of functions H on S to multi-calibration with respect to a different class of functions H prime on T. Okay, so the first thing I want to do is prove like a sort of simple statement. It's really just a syntactic transformation that sort of says, look, if you're multi-calibrated with this one set of functions on S, then you're going to also be multi-calibrated with respect to this other transformed set of functions on T. The transformation will sort of be the obvious one relating to the propensity score reweightings. Okay. So what is that statement? So again, as always, suppose I've got a source distribution and a target distribution that share the same conditional label distribution. Okay. And suppose that the L1 calibration error, let's suppose that I've got a model F that is alpha approximately L1 multi-calibrated on some class of functions S, some class of functions H, and the source distribution. Then I claim F is also alpha approximately L1 multi-calibrated on this other function, on this other class of functions that I'll call H S to T, and the target distribution. And what is H S to T? Well, this is just the set of all functions defined as H of X over the S to T propensity scores evaluated at X, such that H is in my class big H. Okay. So this is the claim. If I'm approximately calibrated on the source distribution with respect to some class of functions H, doesn't matter what it is, then I'm also approximately calibrated, multi-calibrated on the target distribution with respect to like a transformed set of functions where the transformation has just taken every function in H and divided it by the propensity scores. Okay, so the claim clear. So this is some other class of functions. It might be a weird class of functions. Like who knows if this is meaningful or not, but this is like the statement. Okay, and it's basically just a syntactic transformation. Let's start with what we know. Okay, we're multi-calibrated on the source distribution with respect to H. So that means for every hypothesis little h in my class big H, my L1 calibration error with respect to H on the source distribution is at most alpha. Okay. Well, what is my L1 calibration error? That's just the sum over all of the values in the range of my model of the probability that we see that value times the absolute value of the expectation under the source distribution of h of x times y minus v, given that my model predicts v. That's just the definition of L1 calibration. And now, all I want to do is multiply by 1. Okay, so I'll just multiply each term by the S to T likelihood ratios divided by the S to T likelihood ratios. Okay, so I'll just multiply and divide by the same thing. To rewrite this as the absolute value of the expectation still under the source distribution of the S to T likelihood ratio times h of x over the S to T likelihood ratio times y minus v, conditional on f of x being in v. Okay, and I haven't done anything interesting here. All I've done is I've multiplied by the S to T likelihood ratio and then immediately divided by it. So I didn't change anything. But now we've got, like each term in this sum is an expression of the form that we've just been thinking about, right? It is the probability of landing in some set S. That set is just a level set of the model F times the expectation of, taken again over the source distribution S, of some function of X and Y. We didn't care what that function is. In this case, it's this goofy looking thing. Conditional on landing in this set S. And this goofy looking function, it's weighted by propensity scores or by S to T likelihood ratios. Okay, so what does our lemma say? Our lemma says, okay, well, this is computing the same thing as if I didn't reweight things. And instead, all of these probabilities, rather than being taken over the source distribution, were taken over the target distribution. Okay, so like the first lemma we proved in class now says, okay, this is the same quantity as the sum over all of the level sets of F of the probability of falling in that level set. Now, not the probability under S. Everything previously was the probability under S. Now the probability under T times the absolute value of the expectation, now not under S, but rather under T, of f of xy, which is this thing, right? H of x over the S to T likelihood ratio at x times y minus v, conditional on landing in this level set. And this is just the definition of the L1 calibration error that F has with respect to this new function H over W S to T under the target distribution. Okay, so basically just a syntactic transformation. But what we see is that if for every function H, our calibration error was small under the sorts distribution, then for the corresponding reweighted function, H over the propensity, the particular propensity score, the particular likelihood ratio from S to T, our calibration error is small under the test distribution. Okay, and it's just because, you know, like when we perform this trick of multiplying and dividing by the same thing, we've now reweighted this goofier looking function by a likelihood ratio, which you know, does the job of changing the distribution over which we're computing this calibration error. Now, let me state a corollary of this before we take a break and see sort of what this can be useful for. But here's like one immediate corollary that follows from just like staring at this. So suppose that F is alpha approximately L1 multi-calibrated with respect to some source distribution S and some class of functions H. And suppose also that it happens that the S to T likelihood ratio function is in this class H. Then F is also calibrated, alpha approximately calibrated, under the target distribution. Right? Because this theorem says, you know, we started off, we said we were multi-calibrated with respect to H on the source distribution. So, you know, we're actually multi-calibrated on the target distribution with respect to this goofy class of functions, H, S to T. But one of the functions in H, by hypothesis here, is the S to T likelihood ratio function. And if we plug that in for H, we realize that we're actually multi-calibrated on T with respect to some class of functions that includes the identity function. Which means that, in particular, we are regular old calibrated on T. Okay? And the interesting thing about this is that if we take H to be some expressive class of functions, perhaps H is the class of functions that we were planning to use anyhow in order to learn likelihood ratios, right? Like maybe our initial plan was we were going to find some target distribution, we were going to learn likelihood ratios using some class of models, some set of statistical or machine learning techniques, and, you know, we'd cross our fingers and hope that we could do it to small enough estimation error. Well, you know, that plan would have worked for some distributions, those distributions for which it actually was possible to learn likelihood ratio functions using this class of models H, and it would have potentially failed for other distributions for which the class H didn't contain the likelihood ratio functions. Right, but that approach would have required that we know ahead of time the target distribution so that each time we could like solve this learning problem. This is saying, well, okay, Suppose we take this class H that we had lying around anyway, defined by our, family of statistical techniques. And what we do with it is we learn a single model F that is multi-calibrated with respect to this class H. What we know now is even though we don't know T ahead of time, like simultaneously for every model T, simultaneously for every target distribution T, for which this likelihood ratio learning approach would have succeeded, even though we didn't see it ahead of time, we know that this single model F is already calibrated on that target distribution T. Okay. So that's kind of neat because, now instead of solving this likelihood ratio learning problem sort of on a case-by-case basis for each new target distribution that came our way, we sort of solved a single learning problem up front, which, remember, last class we just reduced to learning regression models over H in the first place, so not actually harder than solving the sort of case-by-case problem of learning the best function in H. And we sort of got some guarantee for every distribution this would have worked for. Okay, now we got some guarantee. We got the guarantee with calibration. Okay, so we'll talk after the break about what you can do with a guarantee of calibration. But this is sort of the, to the extent that calibration is useful, and we'll talk about a few ways in which calibration is useful for out-of-sample distributions after the break. This is kind of neat because we got a single model that is simultaneously going to have guarantees for all sorts of target distributions that we didn't train it on. Okay, so it's 3:05. Why don't we take a 10-minute break and come back at 3:15, and we'll talk about why that's useful.
Very familiar.
Perhaps from reading the paper.
Which
No, this is a paper by Michael Kim and Omer and Shafi Goldwasser in PNAS called Universal Adaptability.
that one. Yes.
Okay, so while you were all doing whatever it is you do during your break, I snuck a little natural addition to the corollary. So not only is it that if you were multi-calibrated with respect to some class of functions H that contains exactly the propensity score reweighting from S to T, the likelihood ratio reweighting from S to T, in which case you are calibrated on DT. But even if you can, even if your class H contained any function that was close in this error metric we defined to the propensity score, to the likelihood ratio reweighting function, well, you're still approximately calibrated on DT, and your calibration error relative to your calibration error on the source distribution has increased only in proportion to the this estimation error of the best fit function in the class H. Okay. So all of this is to say if you are multi-calibrated with respect to some class of functions that is rich enough to contain the likelihood ratio reweighting functions with respect to many different distributions T, then this single model that you have learned will simultaneously be calibrated, not just on your source distribution, but on many different target distributions dt. Okay. So what good is that? What can we do if we have a calibrated model? And in particular, why is it useful to have a calibrated model on a target distribution, particularly when we don't have labels for that target distribution? So remember, sort of a common case in machine learning or statistics or whatever is, at great labor and expense, you will, from your source distribution, gather labels, right? Gathering labeled data sets can often be quite difficult and expensive. You pay people to label things. The reason you did that was in the hopes of distilling all of the sort of information contained in this labeled data set into a model that you could then go and apply and deploy in domains where you don't have labels and you don't want to pay people for the labels. You want your model to provide the labels. Right, so a common case is that you've trained this model, now you want to deploy it somewhere. Ideally, you're deploying it somewhere such that the examples come from exactly the same distribution, but that almost never happens. So the best way to think about deploying a model is on a somewhat different distribution that perhaps you have unlabeled examples from, but not labels. That's the whole point. You want to predict what the labels are. So there's various stuff that we might want to do if we had labels, things we'd want to estimate if we had labels that we can try to estimate with a calibrated model without having labels. Okay, and for some stuff that'll work. So let's start with the very easiest thing we might want to, maybe the absolute simplest thing we might want to estimate, and we'll see that that works, and then we'll try to get more ambitious. Okay, so we've got this target distribution. We've got unlabeled examples. We don't have labels, but we hope that our model is calibrated on this target distribution because we were multi-calibrated with respect to, the biggest class of functions we could think of on our source distribution, and that was the class of functions we were going to use anyway to try to learn likelihood ratios. Okay, so what's the simplest thing that we don't know about the target distribution? Well, we don't have labels. Maybe the simplest thing we don't know about the target distribution is what is the expected value of the label. Okay, so let's see what we can do about that. So here's the claim. Suppose on our target distribution, our model satisfies L1 calibration error at most alpha. Okay, so the conclusion of this corollary actually holds. So we're calibrated on the target distribution. Then, well, the thing we wanted to know on the target distribution was what was the average value of the label, but we can't compute that because we don't have labels on the target distribution. But what we can compute if we have unlabeled data, just X drawn just from the feature distribution, the conditional feature distribution of the target distribution, is what is the average value of f of X? What's the average prediction of our model? Right, if we just have features, we can compute this, we can't compute that. But if we're calibrated, then the thing we can compute is a good approximation for the thing we can't. Okay. Okay, so this is almost by definition of calibration. So let's just write it out. Right, so what are we assuming? It's that our L1 calibration error in the target distribution is small. Well, what is our L1 calibration error? It's just the sum over all of the values in the range of our model of the probability of predicting that value times the absolute value of the expectation y minus v conditional on predicting that value. Which is just the sum over all of the values of the probability of predicting it. I might as well move the absolute values. I might as well include the probability inside the absolute value because I know the sign of the probability. Probabilities are non-negative. And I can write this as the difference between two expectations, the expectation of y given f of x is equal to v. And then I have another term I need to account for that's also multiplied by the probability that f of x is equal to v, but this other term is a constant, so it's just times v. Now, I've got these absolute values inside the sum. I can always take the absolute values outside of the sum, and that's only going to make it smaller because that's going to allow for cancellations that might not have happened otherwise. So this is only larger than the absolute value of the sum over all values v of the probability that f of x is v times the expectation of y, given that f of x is v, minus the probability that f of x is v times v. And this is just the absolute value difference between the expectation of y, right? This is just the expectation of y. It's the law of total probability, the probability for each value v, and this is a partition of the space, times the expectation of y, given that we predicted v. So this is just the expectation of y. And similarly, this is just the expectation of f of x, right? It's the probability that f of x takes each value v times the value it takes, v. Okay, so that's it. Okay, so that's, maybe it's not the most sophisticated thing, but it's something you can do on T that you couldn't have done naively because you don't have labels for the target distribution. But if your model's calibrated, which remember it will be if we were appropriately multi-calibrated on this first distribution, then despite the fact that you don't have labels, you can estimate the frequency with which you have positive labels, or more generally, the expectation of the label. Okay. So far, we haven't assumed anything about the label space, right? The labels could be arbitrary real numbers. But for the next application, I want to assume that the label space is binary. Okay, so our model is trying to predict some binary outcome. It will rain or it won't rain. This person will develop sepsis within the next 24 hours, or they won't develop sepsis. Yeah, whatever. There's lots of things that can happen or not happen. Okay. So for everything from this point onwards, the label space is binary. So I want to think now generally about actions that you might take as a function of the predictions that you've made and the costs or consequences of those actions. Okay, so like, presumably you hope to use your model F for something, right? Like F is predicting the chance of rain tomorrow, and you're going to decide whether to bring, how to deal with that. Like you could wear a raincoat, you could bring an umbrella, you could wear a big floppy hat, you could do any of these things in combination. You could wear like galoshes that come up to your knees, and these things will have costs that you will measure according to some loss, depending on whether it rains or not, right? So maybe you're perfectly happy like splooshing around your big floppy hat and your knee-high galoshes if it's raining, but you feel especially silly doing that if it doesn't rain, or maybe you don't mind, right? You can imagine different cost functions. Okay. So more generally, I want to think about an abstract action space A. Okay, A doesn't have to be binary, although it could be, right? Like a natural thing you might want to do, given your prediction for the probability of the label being 1, is you might want to predict the label, right? So your action space might just also be a binary prediction, like 1 or 0, and you'll measure your success just with your classification error. But more generally, the action space doesn't have to be binary. The action space could be more complicated. It could be, what combination of umbrella and floppy hat and knee-high galoshes and raincoat do you wear? Okay, arbitrary action space. Okay. Fix an action space and a model. Yeah. Mapping features to predictions. It's natural if we have a binary outcome space to think of these predictions now as being the probability that the label will be 1, which is the same thing as the expectation of the label in a binary action space, in a binary label space. So a policy of F is any mapping rho from a prediction that F might make, which is a number between 0 and 1, to an action. Okay? And the idea is it tells you which action to take. That action is rho of F of X as a function of the prediction. Okay, so the idea is the weatherman tells me the probability it's going to rain tomorrow. I decide as a function of that how ridiculous my combination of rain gear is going to be. Like if it's 100% chance of rain tomorrow, I put everything on. Maybe if it's only a 30% chance of rain, I still wear my floppy hat, but I don't do other stuff, right? And in general, a policy is any rule for telling me how to act as a function of what the prediction is. Okay. So a policy tells me how to act. How do I think about whether I've chosen good actions or not, or more generally, if my policy is any good? So let's say we've got an action space. So fixing an action space A. A loss function L maps an action together with a label and the labels for this part of the class are just binary, 0 or 1, to a number, which is like the loss that occurs for the action that I took given what actually happens. Okay, so given the getup that I chose to wear and the fact that it actually rains, what is my loss? Or, given the getup I chose to wear, given that it actually doesn't rain, what is my loss? Okay, so further, given a distribution, D and a predictor, F, the loss of a policy which I will write as L, that's the loss function of the policy rho, the model F, and the distribution D, is just the expected loss when I draw a sample from the distribution of the loss that I experience when I apply policy rho, right? So the point X is sampled, my predictor F makes a prediction, and I choose an action as a function of that prediction by applying the policy, and the label Y results. Okay, so this is the loss of a policy, right? Like if I have a way of measuring how unhappy I am given the action that I take and given the outcome that occurs, then if my plan is to follow a policy rho, which tells me what action to take as a function of the prediction, this is the expected value of the loss I'm going to experience when I put that policy into action. Okay. So in general, like if I want to minimize my loss, for example, I want to make predictions that frequently match the label. If I'm in a machine learning context and I have 0-1 loss, where I experience loss 1 for predicting the wrong label and loss 0 for predicting the right label, or I want to sort of minimize my, loss when it comes to flopping around in my galoshes and hat. I want to pick like the policy that's going to minimize my loss if the only information I have to go on is the predictions of my predictor F. But to estimate this thing, I could just directly estimate this thing for a particular policy if I had sample access to this distribution, meaning X and Y pairs. Right? If I had X and Y pairs, I could just compute this quantity and sample. What's the loss of this policy if I follow it? But remember, we had labeled examples for our source distribution. That's what we use to train f of x. But for our target distribution we're deploying it on, we probably don't have labeled examples. We only have unlabeled examples. So I cannot compute this, right? Because this is an expectation over like a target distribution that involves y's. So the question is, what should I do? If I want to figure out what is the best policy to deploy on this target distribution, the minimum loss policy, I need to be able to estimate the losses of particular policies. And so I want a way of doing that. Okay. So suppose I can sample X's, but not Y's. Like, how can I estimate the loss of a policy? Well, remember, I do have this function f that ideally purports to be the true conditional label expectation conditional on X, right? Like f of X in an ideal world is supposed to be the probability that Y is 1 given X. And if I really knew the probability that Y was 1 given X, then for any X, I could compute the expectation over Y, which depends only on this one number that I don't know. What is the probability that Y is 1? Now, even on my source distribution, f of X was only multi-calibrated. It didn't really tell me what was the probability that Y was 1 given X. And on this target distribution, at best, it's like regular calibrated. But nevertheless, I could think about how I would estimate the loss of the policy if f of X was perfect. If f of X actually told me what was the true probability of Y given X. Okay. So let's say the F estimated loss of a policy rho is, I'll write it as L tilde of rho F D, meaning, I'm hoping it's equal to this thing, but I'm putting this tilde on it to let you know that I'm engaging in shenanigans and like it might not be this thing. Okay, so what's the F estimated loss? Well, it's the expectation, but now the expectation is taken only over X. Okay, so I'm taking the expectation over a sample just from the conditional feature distribution. This is something I do have access to for my target distribution. And now if I wanted to compute this, I'd have to, nest, I have to have another expectation nested within here, the expectation of Y given X. Now Y is binary, okay? So I can just write out what that is under the false premise that f of X is the probability that Y is 1 given X. It's probably false, but the expression I'm going to write out would be the expectation of Y conditional on X if it weren't false. Okay, so what will I write out? Well, f of X, that's supposed to be the probability that Y is 1 given X, times the loss that I would experience following the policy if the label were 1, plus 1 minus f of X. This is supposed to be the probability that the label is 0, times the loss that I would experience following the policy given that the label was 0. Okay. So note that if f of X really was the probability that Y was 1 given X, then L tilde, right, the loss with the tilde denoting shenanigans really would equal the loss of the policy. These would just be, this would be a rewriting of the same thing. Okay, so if I really had the true conditional label probabilities encoded in my f of X's, I could evaluate this expectation, the loss of my policy, which requires both X and Y pairs, by taking an expectation just over the feature distribution, which is something that I can do. Okay. And the claim is that actually, if I want this to be a good estimate for the loss of my policy, I didn't need that F was the true conditional label distribution. All I needed was that F was calibrated. Okay, so if F is calibrated, then actually for any policy, the F estimated loss is equal to the loss. And so I can figure out what is the best policy to take using only unlabeled examples from X. Okay. So here's the theorem. Let C be the maximum over all actions in my action space of the loss for taking that action if the label is 0, plus the loss for taking that action if the label is 1. Okay, so some normalizing factor, right? So just to give like an example, suppose I'm engaging in a binary classification problem. So the actions I can take are also 0 or 1. I predict 0 or I predict 1. And my loss is 1 if I got the answer wrong, and 0 if I got the answer right. Then this quantity C would be 1. Because no matter what the label is, one of my predictions is wrong and the other prediction is right. They can't both be wrong. But more generally, the normalizing factor that's going to be relevant is the maximum sum of the losses I can have for any fixed action summed over the two labels. Okay, so the claim is if the L1 calibration error of a model F on a distribution D is bounded by alpha. Okay, so if this is a target distribution and I was multi-calibrated on my source distribution with respect to a class of functions that contained the S to T likelihood ratios for the target distribution, for example, then the difference between, and this is going to be for any policy, then for any policy rho, if I look at the difference between the expected loss of my policy on the distribution, this thing that I can't estimate because I don't have labels, and the F estimated loss of my policy, L twiddle, this thing that I can estimate just from unlabeled data, that these two estimates differ by at most C times alpha. Okay, this is pretty strong, right? Like I've got this model. In principle, for different target distributions and for different loss functions, the optimal policy might be different. Let's note this is for any policy and for any loss function, right? So I've got my model. The only thing I know is my model is calibrated. Now you tell me a loss function and you tell me an action space. And I would like to know on this distribution that I've never seen labels from before, what is the best policy, the one to minimize the loss? And what is the loss of that policy? So for example, I've trained my model. I know what its classification error is on my training data. I'm curious what the classification error is going to be on the test data. Or, right, that's sort of the simplest possible case where the action space is just 0 or 1. But more generally, for any action space, for any loss function, for any class of policies, the thing I want to do is figure out what is the best policy, the one that minimizes loss, and what is the loss of that policy. The claim is that if F is calibrated, then unlabeled data is enough to answer that question. What do? I just compute the F estimated loss. And that's going to be good enough. Okay. So we'll prove this, but I don't know, this is kind of neat. So but maybe before we prove it, like we stare at it and ask questions about it. Right, so this is strong, right? This is saying calibration is enough to estimate the loss of absolutely any policy mapping predictions to actions, no matter what the loss function is, no matter how complicated the action space is, no matter how complicated the policy is. What is important, of course, is that the policy is a function of our predictions and not of anything else. Okay. But like maybe the most mundane application of this is already kind of cool, which is we've trained like a classifier on some source data set. We want to deploy it, but only if it's not going to be a complete disaster. So we would like to estimate the classification error of our model on the target data set, but we don't have labels for it yet. It's saying that if we're calibrated, then we can do that.
Yeah, but C can be quite big.
C, yeah. So C is like a scale, like, you need something like this, because of course, if I multiply the loss function by 1,000,000, this number is going to go up by 1,000,000. But for example, in the classification error use case, C is 1. Right, you make a mistake or you don't. And in general, like if the loss function is bounded, like, this things can only get so bad, then C is at most 2, whatever that bound is. Okay, so is the theorem clear? And this is, this is just a statement about calibration. Why am I telling you this in sort of the distribution shift lecture rather than like in lecture 1 after before we spent like this whole class studying calibration? This is most interesting when you don't have labels, right? Like in sample, for the source distribution, this wasn't so interesting because in order to train a calibrated model F, we needed labels from our source distribution. And if we had labels from our source distribution, we could have just directly estimated the loss, right? So this is useful for a distribution for which we have features but not labels, but for which we have a reasonable reason to hope that we are calibrated. And in this lecture, we've given what is perhaps a reasonable reason to hope that we are calibrated, which is that if we were multi-calibrated on the source distribution for a rich class of functions H, well, then we're calibrated on any distribution such that there's some function in that class that can approximate the likelihood ratios. Okay, so that's why it's coming up only now. Okay, so let's do it. So let's name some stuff. Let's say that KV is the name we give to the probability that f of x is v times the absolute value difference between the expectation of the label given that f of x is v and v. Okay. Now remember, like the one thing we assumed about f was that it had good L1 calibration error. Which means, right, what was the L1 calibration error? Well, that's nothing more than the sum over all of the values in the range of f of this thing that we just defined as kv. It's just the sum of these terms. And the assumption is that this is at most alpha. Okay, so these are a bunch of non-negative terms that sum up to at most alpha. Okay. And so now we're interested in bounding the expected loss of some policy rho of f of x and the label under the true label distribution, the true feature label distribution. Well, what is this thing? We can expand it out. as the sum over all of the values that f might predict of the probability that f does predict that value times the expected loss of the policy given that f of x really does predict that value. And we can expand that out even further as the sum over all of the values of the probability that that value gets itself predicted times the loss if we apply the policy at that value. We play the action rho of v, and the label turns out to be 1 times the probability that the label really was 1, given that we predicted v, plus the loss that we would have experienced had we deployed this policy. We'd played action rho of v, and the label turned out to be 0 times the probability that the label actually is 0, given our prediction. And we can further manipulate this sum. And say, look, why don't I accumulate things by action? So I'll first sum over all of the actions A of the loss that I would experience if I played action A and the label was 1 times the sum over all of the values that actually would have caused me to play action A, right? My policy maps values to actions, so some of those values actually do cause me to play action A. So I need to sum over all of the values. I'm just choosing the order in which to sum over them. I'm summing over them in order of what action they cause me to choose. Of the probability that I predict that value. And remember here, we're experiencing the cost of playing that action when the label is 1. So we also need to multiply by the probability that the label is 1, or equivalently, expectation of the label, given that f of x is v. Okay, so this is sort of like the cost of each action when the label's 1. We've sort of accounted for the cost we experience when the label's 1. We have to account also for the cost we experience when the label is 0. So to this, we need to add the sum, once again, over all of the actions of the loss we experience when we play that action and the label is 0 times the sum over all of the values that would have caused us to play that action of the probability that we predict that value times the probability that the label is 0, which is equivalently 1 minus the expectation of y, given that we predict value b. Okay, so I've just written out this expectation in some much more cumbersome form. And the maneuver that I want to carry out now is I want to say, okay, Every time I have an expectation of y, given f of x is v, I'd like to swap that out for v. Right, like that's what a calibrated predictor is supposed to, that's the property a calibrated predictor is supposed to have. It's supposed to be that, you know, the expectation of y conditional on f of x is v. Now I can't like just do that because I'm not perfectly calibrated, but I can do it while experiencing some additional error kv, right? Because if I swap, you know, saying if I swap the expectation of y with v, and then multiply by the probability of v, which is what's happening, what's going to be happening here. Because if I swap the expectation of y with v, I'm here multiplying by the probability of v, that I have incurred an additional error term of at most kv. Okay, so that's the next maneuver. So this is at most the sum over all of the actions of the loss of that action times the sum over all of the values that would have caused me to play that action of the probability that we predict that value times v. I've swapped this out for the expectation, plus an additional error term that is at most kv. Plus the sum over all of the actions, the loss that I incur if I apply that action on the label is 0, times the sum over all of the values that cause me to play that action of the probability that I predict that value. Again, I'll swap out the expectation for v, so now it's just times 1 minus v. And once again, I pay kv for having swapped out the expectation with v. Okay. So just rearranging things into a more familiar form. This is equal to, you know, just bringing once again the sum of the values to the outside. Probability of making each of the predictions. Times v times the loss of the prediction when I apply my policy rho and the label is 1, plus 1 minus v times the loss of the prediction when I apply my policy rho and the label is 0, plus the error terms. So plus the sum over all of the values of kv times the loss of the action that I play when I predict v when the label is 1, plus the loss of the action that I play when I predict v when the label is 0. And what is this? Well, this is just the f estimated loss of the function, right? It's an expectation now only over x. All of the probabilistic statements are over x. And for each x, what we're evaluating is v times the loss of the policy when the label is 1, plus 1 minus v times the loss of the policy when the label is 0. And that was what we defined as the F estimated loss of the function, and is something that can be evaluated using only unlabeled data. And what is this error term? Well, it's just the sum over all of the KVs, which we know sum to alpha, plus this term, which is the loss of some action when we play 1, plus the loss of the same action when we play 0, which is upper bounded by C. And so this whole thing is at most the L, or is at most L twiddle, the F estimated loss of the policy rho plus C times alpha. Okay, and you can run the derivation in the reverse direction as well to get the reverse inequality, because the only inequality we used was swapping out the expectation for V, but you can also do it in the reverse direction. Okay, so this is sort of, yeah, like giving you a set of things you can do sort of out of distribution on an unknown test distribution that you only have unlabeled examples from, under the premise that your model is approximately calibrated on that distribution. Okay, of course you can estimate the frequency of the y's, but more than that, you can estimate the cost of any policy of your predictions as measured by any loss function. And so in particular, like, like for particular loss functions that you've committed to, like, the classification error of your fixed model, you can do useful things like estimate what is the classification error out of sample and decide whether to use the model or not. But like more generally, since you can estimate the loss of any policy, you can also compute the best policy and use that. And next class, Jess will elaborate on that. We'll end with an exciting guest lecture. Cool. So I'll see you guys next time.
Yeah.